Juarez, please, the stage is yours. Feel free to share your screen, and we are happy to see you, to see what you have to talk to us.
Okay, first of all, I would like to thank you for the pleasure to be here. My talk is concerning few achievements that we have done in the computational material science and chemistry program. Basically, I will focus on this computational investigation of perovskite-based materials. And then, first of all, I would like to thank our founders, sponsors, Shell and FAPESP, and all the institutions that are connected to the computational material science program. Okay, and then I will be happy to deliver the talk after the first talk by Professor Ana Flávia Nogueira and also Professor Camargo, as they already have an introduction on the perovskites. But there's nothing later to say that, for example, as Ana Flávia mentioned in her talk, there's expectation that in 2050, photovoltaics should be responsible for about 30 to 32% or even more or even less of the energy resource for the world. And then it needs new solutions. And then perovskite materials have been, one of them have been raised in the 2020, have reached efficiency nearly to 25%. If I show here in the background, the example of those structures with bases, a combined set of layers with perovskites, glass, and then transparent conductive oxide, and so on. Okay, of course, Ana Flávia will be a lot more expertise to talk about how is the synthesis of those devices and then how the composition affects their efficiency. But what I want to show here today is how we employ computational material science techniques to address perovskite properties and to understand, to improve our understanding, microscopic understanding on the atomic level. In that sense, right here, as shown before, the perovskite materials, like with the chemical composition ABX3, when you have the cations and the highlights, and then that particular case, we are talking about chlorine, bromine, iodine, and then for X and B, some materials from the chemical species that has oxidation state to 2+. Most of the case is lead, which is, we know that has some health concerns. And then for the A cation, we have the famous cesium and also alkali metals, but we also have more organic molecules like methyl ammonia, pyridinium, ammonia, and so on. Okay, those possibilities on that particular structure here that we'll show here, that gives for us the possibility to really control the composition. Then you can really do some band gap engineering or material science engineering by changing the composition. And this is really one of the crucial points in the perovskites studies in which people have been exploring for quite some time already, because it's possible to combine different types of cations to inorganic or organic cations, the monovalent ones, and out as well as the bivalent ones. Furthermore, also the highlights too. And then our goal here is to understand the atomistic properties of those systems. It's important to say that in August of 2018, we don't have no knowledge on the perovskite business, because it was not a material that we was studying for that time, but we were doing a lot of different materials. But in that particular case, I want to say for you today here that after 3 years, we have reached quite a very strong understanding. Here, for example, one of the first studies that we did, that we decided to do it, because they were inspired by this possibility of the control the composition. The first study that we did is to study the structure, electronic, and stability properties by using inorganic perovskites with the composite ABX3, as I mentioned before, by combining potassium, rubidium, cesium with germanium, tin, and lead with the highlights, the chlorine, bromine, iodine. With these three rows, these three vertical columns of the periodic table, we are able to compose 27 different types of perovskites. And we want to understand how their properties change. Because it is a very basic study, but it's important for us to start at some point. And then we start on that, then we was able to establish a correlation how the cohesive energy of those materials change as a function of the highlight. Like for chlorine, as you can see here, the cohesive energy means gives the stability of the system, EU changes from iodine enhanced towards chlorine, okay? Is because of the effect of the a strong Coulomb interaction among the effective charge that is located on these different species. But as you can see, when you change the monovalent cation, the difference in the cohesive energy is basically almost null. There's not too much difference. It does not affect the stability, but the highlight really plays an important role. And then for look at the stability one, we move to the electronic properties. I show here an example of the band structure for you. I see on your left, on your right on your screen. As you can see here, is a material that has a semiconductor behavior, which should be expected like that, otherwise we will be in trouble. Okay, but then we identify all the components of the state that plays the role. And as you can see here, the highlights P states play a very important dominant role in the top of the valence band. And then also different composition of the states too. And then show here on the right side here, as you can see here, the right on the bottom here, we show the electronic band gap, at in that particular case, at the R point, okay, because this is an ideal complete structure. And then you can see that you can tune the band gap by changing the chemical composition. Not so, by changing the chemical species. That is going from chlorine to iodine. As you can see, there's a reduction of the gap, and all the system follow the same trend if you change the monovalent cation or not. It means the following. The cation really is not playing the determinant role to drive the change in the band structure. However, in case of smaller numbers of the change, like 0.1, they are important. But the largest changes comes from those species. And then, of course, this one was done based on the ideal cubic structure. But, however, we realized later on that distortions on the structure plays a very important role. Okay? In what sense? In the sense that you have a perfect octahedron. Before, in the previous study, we have a perfect octahedron. But now we investigate now how the distortions on the octahedron can affect the properties, electronic, excitonic properties, structure properties. In that case, we investigate the Jahn-Teller effect, okay, that you have 6 bonds around the cation, the bivalent cations there, and then they are equal size, but then you make them 3 longer and 3 shorter, and you create a Jahn-Teller distortion. As you can visualize here, what you can see is that this structure has elongate octahedrons, or you can make a displacement in the monovalent cation too, and then make a rotation out of phase or in phase of the octahedrons. And then beyond of that, we also can consider different structures, like hexagonal phases 2,8 and 4,8, in which the octahedrons are not fully interconnecting all directions, and it gives some like a lower dimensional perovskite structures. By doing those investigations, all the properties to consider a large number of structures, we consider in that particular case the prototype of cesium germanium X3 when you change from chlorine to bromide and iodine. This was very important. And then they pick up one of the systems, and then here I show for you how the band gap changes as a function of the volume. Look at those compositions. What you can see here is quite very clear. For example, if you look at the bottom figure, we'll look at the bottom figure first. It will help us better. Just for you to have to get the insight from here. In the first figure here, when you have with the label 1, the Roman label 1, we have ideal structure. It has a band gap of 1.6. Okay? Keep in mind that this band gap is a DFT band gap. We have some small area compared experiment, but what we have to look here is the changes. Then you have the structure, the ideal structure, no distortion, perfect one. The band gap 1.6. Once now we go for the figure on the third figure, the third Roman here, they have a band gap 2.8. And this structure has a distortion of the octahedron. It's a Jahn-Teller distortion. It's a cubic line, but it's a Jahn-Teller distortion. The band gap changed from 1.6 to 2.8. To understand who is responsible for this effect, because when you change the structure, we also find that there's a reduction in the volume, okay? So there's an increase in the volume in that particular case. And then what we did, we picked up the ideal structure and then calculated the same volume as the last one. and then you got a band gap of 2.14, which gives the idea for us how is the change in the band gap when you increase the volume, okay? And then this is very important. Okay, the first thing, the distortion of the octahedron creates an increase in the volume effect, then this increases the band gap, and after that we have a distortion on the octahedron that's responsible for the breaking the symmetry and gives for you an additional increase. This happened in particular case for this compound cesium here. And then on the A figure, the top one, we show how change the band gap as a function of the volume for all the different cases. And we feel these dots that are different, they are outside of the lines of the figure here, they are the hexagonal structures. The hexagonal structures gives a wide band gap, okay? And here I show the absorption coefficient, the total absorption coefficient, where you can see that the ideal structure, because it has a smaller band gap, it is to absorb quite high, smaller cutoff energy, smaller energies, photo energy, but after that you have a displacement because of the octahedral distortion, and for the last one you have the hexagonal structures. As Anna Flávia mentioned at the beginning of the her talk there, what he saying? You start the formation of those structures, they start to form hexagonal phase, and then they go to the cubic phase, which has a quite nice band gap for the photovoltaic applications. However, if some of those grains stays inside with the hexagonal phase, it's going to contribute with a larger band gap. That is quite an important point. And we also find too that excitonic effects does not play as a minor role in that particular case. We use a tight bind approach combined with the FT, as was shown yesterday by Alexandre Cavalheiro Dias. And then here, of course, we was not so happy because we was going to move further to try to tune the electronic band structures. We move now to the systems with the double perovskites. For the double perovskites, we consider in that particular case, the systems here, what system we consider? The system combined between cesium, silver, bismuth, and chlorine or bromide and iodine. The idea here is the following. Can I mix the highlights in the way that you can improve stability or compromise stability? Because you see, before, chlorine has the highest cohesive energy, has the highest stability. But the band gap is going to come to reduce the direction of iodine. And then we take those systems, you perform a large number of calculations to identify how it makes the alloy. And then you create the double perovskite structures. Means we employ a cubic-like model in which you have 8 cesium atoms, 4 silver, 4 bismuth, and then you now have 2 species now, 2 highlights. And then we exchange this composition of 2 highlights and explore all the possibilities, because we chose one small cell because we want to explore all the possibilities. And then from that on, we could come with the nice models and to understand what is happening in the double perovskites. Okay? And then here I show for you here, just to understand one point, important point here, because it's the role, the competition between stability and band gap properties, electronic properties. If you move, you improve stability, but you lose the band gap properties in the direction of photovoltaic applications. And then, as you can show here, the actual cohesive energy with respect to effective charge, which really shows what is driving the stability of those systems. And then, as you can see here, I show here the band gap for you. For the case of the A figure here, the first one is when they combine chlorine with bromide. And then you can see how the band gap, there's evolution of the band gap. When you create the alloy, the volume of the band gap, which is expected, is a well-known behavior for alloy in semiconductor business. And then you move on for the chlorine, iodine, and so on. Okay, then you can fit the band, we can adjust the band gap according to the composition. However, comes the point, how is the stability? Based on the efficiency, by measuring the power conversion efficiency, we use a more simple model, okay? We are able to show it comes to the fully compromise. If we go in the direction of chlorine, we have the highest stability. But the band gap is so high, the power conversion efficiency will be lower. But if you go in the direction of iodine, we have a low stability, but higher power conversion efficiency because of the good band gap. And then you have a compromise that we suggested is a mix of chlorine with iodine. Okay, we can take the advantage of improving stability, but at the same time compromise in the electronic properties. And then we move on. Why we need to move on? because the perovskites, as Ana Flávia showed, and also Professor CaMato showed, is not only organic perovskites. Now we have to explore now the hybrid perovskites. The hybrid perovskites, it opens a new room. It's a Pandora box. Why? And it's more complicated, more complex, because we change cesium for our organic molecule. And then there's a few things that have to be mentioned here. First, those molecules has a dipole moment, most of them. And then what you can have a dipole-dipole interactions. And those interactions are long-range interactions and gives rise to new effects. You create a Pandora and they concern the different phases because the Coulomb interactions can drive, because the system tries to have a primitive cell with a tensor dipole there. Experimental can measure it and come with the primitive cell with only one molecule. But what you are measuring is average of structures, in which all those molecules can be randomly oriented depending on the temperature. However, if you know the temperature, those dipole moments you align to minimize the Coulomb interactions. Second point, the formation of hydrogen bonds between those cations and the organic framework. And this you make that the organic molecule is more displaced in the direction of the octahedron for particular case depending on the termination of the molecule. And along with all those effects come the structure phases. With all those effects together, they will compete to stabilize those structures. It is quite really a challenge here. And then to address that challenge, what we did here, this work, we studied the particular case of with a lead perovskite, iodine 3 with the different cations, or inorganic one and organic cation. We compare cesium with ammonium, methyl ammonium, femimidine, and look how the different orientation of the molecules, how the different, if it has a small distortions, what we find here, that particular case, the distortion of the octahedron is quite small, okay? But there's a difference in the distance between the lead and iodine, they change for pair with respect to cations. Then, what I call your attention here is the absorption coefficient, because this is what measures what happens. What this case will show here is basically the following. All the cations basically, except the case when you have different, one of the molecules that really change the structure and affects a lot, because basically almost broke the structure, because a quite large cation. But the other ones, basically does not affect the absorption coefficient. Okay, but those cations are important for the stability. But concerning the optical properties, there are small changes. Once again, the hexagonal structures, because it is not an interconnect octahedrons, they create a large band gap, and you have a large, the absorption point starts with a large energy. Okay, this is quite, to say, an important point. And then we perform similar study, consider now different cations, and then with a team iodine 3. In that particular case, this work was done by my unit. In that particular case here, what we have done here, we consider methyl ammonium, methylphosphonium, femimidine, three different types of cations, all of them has a dipole moment, which means that we try to explore different phases on the structures and really look the role of the dipole moment. When I minimize this, when I have a structure in which the dipole moment cancels out within the structure because you create different orientations for the molecules, in that particular case, is the energy lower? Yes, that's true. Can it affect the band gap or not? Can it affect the electronic properties or not? From that on, what we find out is the following. Those interactions are important to play the role here, because you have to keep something in mind, very important. The energy difference between the hexagonal phase and the cubic phase, which is a good one for the photovoltaics, it's just about 100 milliV per formula unit. Means it's very small. Sometimes I really how the experimenters can really reach the cubic structure, because the different energies are very small. The fluctuation, temperature effects are quite important. Okay, means it's really important here. And then we show how the stability change without the different phases and different structures, which helps us to understand the quite very deep understanding of the role of the dipole moment and also the hydrogen bond formation. And then we come to the electronic properties. The electronic property that I can tell for you that is amazing is the following. If you take this cation out of the structure keep the structure frozen. Okay, because if you don't take it frozen, it just can collapse. Not collapse, that's not collapse. But to take the structure, take the cation out of the system. Pop out cation, the monovalent cation out. If you calculate the absorption coefficient, is nearly the same. Means who drives the system that drives the absorption are the octahedrons of the system. We perform those calculations to investigate, what we try to do is the following. We make an absorption decomposition to see what part of the crystal that is really make a contribution. And here it comes out, as in different systems too, that the inorganic octahedron really plays an important role in that particular case. The orientations, the different orientations of the organic cations is important for the stability as a dipole moment orientation. However, the absorption coefficient is not strongly affected by that case. However, the distortion of the octahedrons are. And this is what I want to keep in mind for you, everyone, after finishing this talk, keep in mind. And then we come to the systems, and then we move on now for more complicated cases. Now we are, as mentioned by Professor Kamat on his talk, okay, we can explore the perovskite materials. Once we have the control over it, is a Pandora box in which you can explore too much different structures. In that particular case here, what I want to show here is the following. You can have the perovskite, what we call 3D, 2D, 1D, or even 0D structures, based on the interconnection of the octahedrons. Okay? And this interconnection can classify those structures. Our previous discussion up to now was based on the 3D structures. Now we follow up to investigate the 0D structure. The 0D structure was just a suggestion for Professor Flávio Nogueira. This work was collaboration with her group. And then William Oliveira was on her postdoc, was synthesized those materials here. And then we need to ask for us if you could characterize and help to improve our understanding. And then this work was done once again by Mayudi, PhD student in the group. And then what was done here? Those structure, you can see, is quite complex. It's a 0D structure in which there's 2 or 1 octahedron are isolated, are surrounded by organic cations, okay, which balance the charge. Those organic cations, their bond between the atoms are covalent bonds. There's a weak bond, like a covalent bond, not covalent bond, but hydrogen bond and a more cold interaction between the organic cations and the inorganic framework, not that particular case, not frame, but isolate octahedrons. But these structures are quite nice. But then we calculate all these structures. We help to improve the understanding of one of these structures concern the position of the hydrogens, because it was we performed several calculations to improve the IRD, the X-ray diffraction interpretation. We arrived at the conclusion what should be the best structure. And from that on, once we extracted the refine of it, we did down the optoelectronic properties. Of course, I summarize that's the most important results here. The paper that was published contains a lot more results than one shown here. Then what we can see here was the experimental band gap, the optical band gap, goes from compound 1 to compound 3 with the different cations from 2.31 to 3.22. Okay, and our results for compare the relative difference between the systems are pretty good compared with the experimental results. Then we can understand what's important here. And then what we can see here is concern where start the state that really makes the contribution. The gap is small. Because as you can see, the band gap can be quite small here with the vertical line. However, and the B figure, however, the optical band gap, which matters for the absorption, are slightly larger because the density of the states at that particular region are very low number of states, which does not help to improve the absorption coefficient. And then we analyze the effective charge and try to explain in the way, provide explanation how to improve those, understand, concern the stability of those systems. Okay? With that in mind, I come to my conclusion of my talk. As you can see, we explore simple, the basic structures up to the complex structures, and then it provides for us a quite good understanding that the octahedral distortions play a critical role for the electronic structure properties. The competition between energetic stability and band gap engineering is a critical point here. It's really important to say because we can improve stability and electronic properties and can say affect it. To understand the role of the interaction is quite important, especially when you go dipole, hydrogen bond, octahedral distortions, phase transitions are quite really to say a challenge problem. And then the exploration of low dimensional perovskites, as Professor CaTe says today, as Ana Flávia is also doing too, is something I believe that is a very interesting point and how to explore different those materials for different applications. I show here that the work that was published, okay, and then additional manuscripts are in progress. We hope that concluded soon. And then I would like to thank. First, thank you. Okay, here I have first the balance quite good. We have three ladies here: Mailde, Ana Flávia, Mariana. She also responsible for the first work. She was a scientific work, and our postdocs here: Julian, Sericante, the faculty member Matheus is a part of one of associate members of the group on the project, and also Alexandre that is working in perovskites, also two-dimensional materials, and William Coelho now is faculty member in the Federal University of Minas Gerais that was part of the experimental work that was done together with Ana Flávia, the low perovskite systems. Okay, and then Red open for questions. I just see that Ana Flávia raised her hand. I wasn't imagining that. Okay, then I'm here.
Thank you very much for a very nice talk, Juarez. We have a question from Albert Bittencourt here. Juarez, thank you for your presentation. As commented yesterday, silicon solar cells have efficiency limit around 30%. It is possible to estimate the efficiency limit for a perovskite as well using computational simulations. Otherwise, how one could justify the investment in this research area if there is no guarantee that higher efficiencies are feasible to obtain?
Okay, what we can tell about that is the following. First, silicon, the efficiency is a bit lower than 30%, quite lower than 30%. Okay, I think maybe around 20%, in the case of the number of years. Okay, as Professor CaTe mentioned today, we can explore a large number of different materials. Okay, however, from my understanding, for a new technology to take places, okay, it needed really to separate silicon a lot. For example, carbon telluride, from the point of view, even carbon is a bit toxic, but there are some plants in the world that build up in carbon telluride solar cells. But I think the perovskite have a long place to go. But what's important to realize here is the following. Photovoltaic perovskite is just one of the applications of the class of the perovskite materials. Today, the exploration between low-dimensional perovskites from 3D to 0D is a Pandora box. It can explore in a large number of applications, electronic applications. Then what we have to be here is, I think, we have to be open-minded for some application to justify that why we are studying those materials.
Thank you very much, Juarez, to clarify that. We have time for only one more question, since Pablo and Rubens also raise his hand, and Ana as well, but they asked in the previous one. Ana, go for it, and the other guys ask straight to Juarez later on.
Okay, thank you. So, Juarez, is amazing the amount of data that your group achieved in the last years concerning perovskite. So my question is, for instance, for MAPI, the most known perovskite, when you go from like a cubic to orthorhombic, tetragonal, although we see some changes, slight changes in the band gap and also in mobility, if you put them on a device in the operando conditions, you don't see much difference in device performance, even going from cubic to orthorhombic, okay? But in the first example that you mentioned with cesium, germanium, and allied, okay, when you have these octahedron distortions, you go from like a band gap from 1.6 to almost 3 electron volts. There's a huge difference in terms of band gap. Are you aware about any group that have tried to prepare those perovskites? And if yes, it's possible to predict which one is going to be the most stable in terms of the thermodynamics, because of course the cubic is the ideal one with a band gap of 1.6. Although when you have these distorted octahedra, you go up to like 3 electron volts. You don't want those, at least not for photovoltaic applications. But the question is, when you're preparing those materials in the lab, maybe you end up not with the cubic, that's the ideal one, but with the distorted one that has a really high band gap. Can you comment on that?
Okay, first, concerning the experimental part, I'm not aware, but we're not aware. However, the following, those distortions does not appear on all the systems. If you take the metacap, like the map, we don't see those distortions, okay? However, what I'm trying to do now, what I'm trying to do is this exactly now, we are starting it. We're going to take a real perovskite that we are using the real perovskite, the alloy, cesium mixed with fermimidine, lead, and mixed now bromide and iodine with the right proportions. The large cell, supercell, and to investigate how those effects come together. Why? In the ideal structure, I believe, you don't have the octahedral distortions or the map. However, when you put these alloys, different size, different things, my feeling that there's a competition between all those effects, between dipole-dipole interactions, hydrogen bonds, octahedral distortions, and all of those that gives for you at the end your electronic properties. But now, who is driving what? And then if you change, say, from the cubic structure or the octahedron that are now, because the small energy difference, they are nearly the same. But what effect that's really driving the electronic property, from my understanding, is still not fully clarified. Because
it's so. Can I just have time for just one more question?
Sure, yes, you can.
Very quick, a quick one.
You are the boss, so go for it.
Just a quick one. This because it includes the batteries group. So our cars run with batteries that are made with lead. Perovskite, the most efficient solar cells, perovskite solar cells are also contain lead. When you go to tin, we have a problem because of the oxidation from tin 2+ to tin 4+. Okay, this does not happen with lead because of the relativistic effect of lead. So if you compare the batteries, the lead in the batteries, and with the lead in the perovskite solar cells, we think that the stabilization of this 6s2 orbital is actually the one that's playing the role here in terms of electronic and optical properties for the perovskites.
If you look at the relativist effect on the lead, I would say that it has a point, because the relativist effect makes the inner state to shrink, and then the S state is going to expand. It'll be more delocalized. This it will play some role. Now the point is when you talk about tin, the facility that tin change the state from 4 to 2 is much easier. And then these octahedral distortions can even make this to be easier. Because if you change the state, you go from a coordination of 6 to a coordination of 5. And if you can balance that, and then you have some point. If you have a lot of distortions, the tin will be a case to change the state. That's true. But in that case, not relativist effect, but the structure problem might be the case. Because you don't need to change the coordination from 6 to 4 to change the oxidation state. You just need to have something to balance the charge. And then between 5, then you can do it. But my feeling and the understanding that we gained in the last, 3 years on that particular problem, that temperature effects, those dipole moments, hydrogen bonds, octahedral distortion, all those effects are on the cell. The point is that this is why I've had the feeling is one of the reasons that the best efficient cells are with this combination of the alloy. Cesium, fluorine, brom, bromide, iodine, because when you combine all those things, you reach a particular structure, level, stability, then that gives for you the best that you can get, obtain. Only because of it, otherwise not working.
Thank you very much, Juarez.
Thank you,
It was
Juarez.
such a great discussion. So happy to see that. That's the point to having this workshop. So find the time to discuss and